All right. Thank you all for coming today. I'm Kostas Ferles. I'm the CTO of Veridise. We're a Web3 security company. And today I'm going to be talking about ZKVM determinism that lasts and how we can go from just audits to continuous and provable security. But before I do that, I want to tell you a story about the life of a ZK developer up until now. And spoiler alert, things were a bit chaotic. So let's first meet the heroine of our story, which is a modern-day ZK developer. And during her quest, she has to write low-level circuits in a very complex system like a ZKVM. She has to do that in a very low-level language. She has to do a lot of optimizations. She has to ensure that everything is secure. And often she has to do that with little to no dev tooling support. I don't know about you, but like I wouldn't want to be in her shoes. And of course, there are no story without villains, and she has like a lot of them, starting with her product manager, who wants everything delivered fast, secure, and let's be honest, like he doesn't have like many technical insights. Then there is this creature called an auditor. Full disclosure, I'm one of these creatures. And our job is to find as many bugs as possible in a very limited time manner. And when we're done, we just throw everything back to our heroine. She has to fix everything. This slows down a lot. And because of the complexity of the systems we review and the limited time frame, we can have kind of we can be a big budget line in the item of a project. But as you already know, we are kind of like a necessary component of the industry. However, we're not as bad as the real evil of our industry, which are black hat hackers, which the only thing they need is like just a single vulnerability, and then they can steal a bunch of funds from the protocol, and then they can have like very detrimental effects on the future of a project. So how does the story end for our heroine here? Well, not that great. Projects get delayed. Maybe the project will go multiple rounds of auditing. And even after that, there is a high probability that the critical bug will sneak into production. And to make matter worse, if the team wants to introduce some upgrades into the protocol, the whole expensive cycle has to start all over again. But regardless of all of this, she managed to deliver. So in an essence, she's a superhero. But I'm here to tell you today that life doesn't have to be that way. And we want to make her life way better. And how we're going to do that? So we're going to introduce the best character in a superhero story, the humble sidekick. So for our heroine, the humble sidekick that we introduced is our tool called Picus, which helps her prove determinism of her circuits. I'm going to go into detail about what's determinism and why that matters. But let's see how the sidekick helps our developer. So every time she writes a ZK circuit, then Picus will check determinism of these circuits. If everything is fine, then okay, she can continue on with her day. However, if things are not fine, Picus will report this as a bug, then she will fix it, and then the same loop will start all over again. So this turns out to lead to faster development cycles, reduces bug early on, simplifies manual auditing later on down the line, and generally having Picus in the project's pipeline gives guarantees that outlive audits, and they're continuously enforced through CI/CD. And this story doesn't live only in our imagination. We have applied this kind of new way of developing ZK circuits and ZK VMs during and after our engagement with Risk Zero, when they came to us to audit the circuits of their ZK VM. I'm going to go to more details about this in a bit, but first, let's see why proving determinism matters. So first of all, let me give you a very quick definition of like what is a determinism in the context of ZK circuits. So you can think of a ZK circuit as providing an interface to users that they can use to generate proofs about the execution of a program. So for example, this let's take this very simple circuit API that let a user prove their balance. So on a high level, you can think of this API as having a single input, the user's address, and a single output, the balance. So generally speaking, in most cases, when developers develop a circuit, their intention is to have a deterministic function from the inputs to the outputs. So for this specific case, for every possible address, we want at most one balance to be provable. However, the problem is that in today's ZK development world, it's very easy for developers to essentially introduce relationships instead of functions. So here, a bug of that sort would allow somebody for a single address to prove that it has like, two balances. And so imagine an attacker that can prove that like, it has two balances, bet your money, they will choose the bigger one. And usually in this context, the bigger one is the unintentional one because we work in these very large prime fields. And why this is kind of like, an important problem to solve. So based on our experience as auditors and based on a very recent academic study, these type of bugs are the number one source of bugs in ZK circuits. They are very complex to find. And even when you when you introduce a fix for this type of bugs, it's again hard to verify that like, this kind of like fix actually patched the bug. So we think we need something that is like, automated. So let's go now and see how Picus automatically solves this problem for us. On a high level, the API of Picus is as follows. So it tries to prove that for every input of your, for every input of your circuit, you can only generate proofs that have like a single output value. And the result of Picus can be one of the following. It can verify that your circuit is indeed deterministic, in which case everything is fine. It can generate a counterexample, which is gonna show you the actual bug. So it's gonna show you two witnesses where like, they have the same input and the outputs differ. So you can use that to debug your circuits. Or it might get stuck and like, run out of resources, in which case it will report unknown. However, in this case, it will provide to the user the progress that it made thus far, and then like, users of Picus can use that information to refine the input and then use Picus again. This is a very high level. Let's go a little bit into more details. So internally, Picus uses two techniques in a synergetic way. The first one being a static analysis, which is cheap but can be a bit imprecise. And the second one is SMT solvers, which provide deeper reasoning, but they come with a bit of a premium in runtime execution. So the static analysis phase has predetermined patterns that can guarantee that an output is deterministic. This phase is very cheap and efficient to run, but sometimes it might get stuck. Sometimes there might be some output that doesn't match the predetermined patterns, so that phase might not be able to make more progress. So this is when the SMT solvers will pick up, and they essentially encode the behavior of the circuit as a mathematical formula, and then they generate they try to disprove a proof that proves that the output can have like only one value. But if you have ever used like an SMT solver, this can be quite expensive, and you have to bound their execution, so you can you don't have to just wait for them indefinitely to finish. And these two phases will run in a loop, and as they run, they're gonna create a common database of outputs that are currently being proven to be deterministic. So if one gets stuck, then the other one is going to generate more outputs that are deterministic, and that will lead to the other phase to get unstuck. And this runs at the loop until we run out of outputs to prove that are deterministic. So this is a very high-level overview of how the internals of Picus work. And of course, we have employed several optimizations on how we construct the SMT formulas to be more optimized, to how we break out the proof of a large circuit to subproofs. But I'm not gonna bother you with these details. Let's go and see how Picus works in action. And as I promised earlier, I'm gonna give you a bit more details about the engagement we had with RISC-0 to verify determinism of their ZKVM circuits. So initially, RISC-0 came to us to audit their circuits, and the scope included around 120 sub-circuits. And of course, part of the agreement was for us to verify that all of these sub-circuits were deterministic, and also apply all of our other tools we have for ZK circuits. So let's see how Picus performed. So if we counted Picus as a separate auditor in the whole process, it would have been the top performing one, as it found 9 non-deterministic circuits. And the majority of these bugs were, critical or high. And Picus managed to do that pretty fast. In most circuits, Picus terminated in a few seconds, and it wasn't able to handle, at the time only one circuit. So let's go and see some of the bugs that Picus managed to find. The first of these bugs were in this component called expand U32, which take two inputs, a 32-bit integer and a signed bit. And what it tries to do is decompose this integer into 4 bytes. So the bug that Picus managed to find is that when sign was 0, it was possible to create 2-byte decompositions of the same integer. So the lower one was the intentional one. The one on the top, which is going to be a large number, was the unintentional. So imagine if a ZKVM application was using that to calculate a balance of a user, like I mentioned earlier. So the attacker would have the ability to create a very large number, given the non-determinism bug here. So the second bug, the animation was broken. So the second bug was in a component called doDiv, which, as its name indicates, takes 2 inputs, a nominator and a denominator. And essentially what it does is finds quotient and remainder and expresses number as q times denominator plus the remainder. And the bug here was that this component internally wasn't constraining the remainder to be less than the denominator, and that way you could have 2 solutions to the equation. So for example, you could say that number 2 over 1 can be either q2 remainder 0 or q0 and remainder 2. So imagine if this one was calculating some rewards of a protocol, some fees of a protocol, and an attacker could kind of like essentially bypass paying the fees by selecting the solution that says Q to 0. These are the these are the bugs that I'm going to discuss today, and these are the ones that actually fit in like a single slide. But Picus was also able to find like way deeper bugs that like had both the developers and our auditors kind of like scratching their heads for like hours before they understood what was the actual issue. So it's a very, very helpful kind of like companion as people develop ZK circuits. So after the developers fixed the bugs, then Picus came back in and gave the stamp of approval for every fix, so we knew that like the bugs were actually fixed. And you can find the final audit report in that QR code. And fortunately for us, we didn't end up here. So Risk Zero, after the audit, added support into their ZirGen compiler, which is the language that they use to write their internal circuits. And later on, when we audited their Quetzal accelerator, we again used Picus and provide that the Quetzal accelerator was deterministic. And since then, their CI/CD runs Picus every time they introduce a change into their circuits. As we kept improving, like Picus, it kept finding more bugs. Like remember the one circuit we couldn't verify initially, we found like some issues there, and also it was able to find regressions as the Risk Zero developers were like making like changes into their code. Before I leave you, these were all the details I had to say about like the engagement with Risk Zero and how like Picus works internally. I wanna plug for a few seconds another initiative we have to broaden the applicability of Picus, and this is the introduction of a new intermediate representation language called LLZK, and this has been recently funded by the Ethereum Foundation. And the goal of this initiative is to kind of like unify ZK development, because as you might already know, it's kind of like a bit fragmented because there are like so many different languages and embedded DSLs you can use to write circuits. And this initiative tries to kind of like create a common IR where people can write their own analysis, transformation passes, write their own backends, and also that's where we come in and build like security tooling on top of this IR. So if you lower to that IR, you can run Picus, you can run our static analyzers, and you get all the benefits. So that's all I had for you today. Thank you so much for watching, and also thanks to Risk Zero and Ethereum Foundation for all their support.
Cool, awesome. We have a couple minutes for questions if anybody.
Hi. So you mentioned in the last slide that you were considering to add in support for Plonky 3. How ready is that? How advanced are you on that path?
So yeah, we do have like a prototype already working, and we're like currently working with Succinct to like do the same kind of like exercise, and they're using Plugin 3. So as we speak, we kind of like add more and more support. Yeah.
Okay.
So like yeah, if anybody's interested, we have a booth downstairs. Like come talk to us, and like I'll give you even more details. Yeah.
Hi, thanks for the talk. A more basic question: how did you guys ended up going for the verification of these like ZK circuits and ZKVMs? Was it like a company in this domain that approached you guys, or did you guys see it coming and then went for it?
Yeah. So yeah, we like we are an auditing firm, so like we want to find like bugs or like verify their absence like as fast as possible, and like a few years ago, we entered the ZK space, and then we started like, looking kind of like, what are the most common bugs there, and like, these type of bugs were popping up like, even back then. Then, we did like some research. We published like, the initial version of Picus, and afterwards, like, like as we get more clients, we saw that like, this is kind of like a real issue. So we kept like, working, like, kept improving like Picus. Yeah.
I'm sorry, time is over. We can
Okay.
have more questions.
All
Thank
right.
you.
Thank you.